Hello, in this video we're going to give an example of how to use the tools of differentiation to thoroughly analyze a function and its graph. You might take a look at the table on page 248 in your textbook. It lays out a list of things you might want to consider when you're analyzing a function or a graph. We'll do many of those steps in this particular example. So we're going to start by looking at the function given by y equals f of x equals 4/3 minus tangent x. We're going to consider this only on the domain minus pi over 2 to pi over 2. That'll prove to be important. And we'll see how the tools of calculus can help us better understand this function and its graph. So we have these great tools, these graphing calculators. So if you're faced with a problem like this, by all means graph it. And then we'll use the graph, often refer to it to guide our use of algebra, trig, and calculus to fill in whatever details you wish about the graph. So one of the first things you want to think about is intercepts. These are always good to display if you can. There are two kinds of intercepts when you look at a graph, the x-intercepts and the y-intercepts. The y-intercepts are the points where the function crosses the y-axis. And we can get those by setting x equals 0. So that's usually a pretty easy, well, you hope it's going to be a pretty easy calculation. If you plug x equals 0 into the function f, we get 4/3 0 minus tangent 0 gives us 0. And so that gives us a y-intercept at the point 0, 0. And of course, we can see that very clearly on the axis that the graph passes through the origin. The x-intercepts can be a little more difficult, and they are in this case. For x-intercepts, we set the y-coordinate equal to 0 and try to find the solution, the x solution to this equation. And the solutions here would then give us these places where the function crosses the x-axis, which are always nice to know too. Now, in this case, of course, we already have one of those crossing points. That's here, and it's not hard to see when y equals 0, the x equals 0, of course, is one solution. We already know that. Unfortunately, the equation 4/3 x minus tangent x equals 0 is not one of the standard ones we learn to solve in algebra. It is not a polynomial, so we're not going to be able to have much luck with factoring. So generally in cases like this, we either hope they work out really nicely, say with trig functions, coming up with angles that we are familiar with, and if not, there's really not much we can do about solving the equation. At this point, about the best you could do, and I'll leave this to you, would be to zoom in on the graph and use your tracing function, and by zooming in, you might find the coordinates of these intersection points, these x-intercepts, to a bit more accuracy than we can see them from the graph here. At the end of this chapter, when we study Newton's method, we'll see a very quick analytic method for coming up with very good approximations to solutions of equations like this. So for now, we're just going to say, yes, there's a couple more intercepts there, and I trust you can find them, or at least find good approximations to them on your calculator if you needed to do that. Now we know the tangent function, its graph, has asymptotes at plus and minus pi over 2. And we can see hints of these asymptotes in the graphs over here. So on the left, the graph appears to be heading up to plus infinity, which suggests we might have an asymptote right there. On the right, the graph heads down to minus infinity. So perhaps a vertical asymptote over there like that. So if you suspect asymptotes, you really want to verify them with some analysis, because a graphing calculator cannot show a complete asymptote. This may just mean, over here, it just may mean the function is going up for a while, but it's going to come back down. So if you want to assert there's an asymptote, there's no substitution for doing the analysis. So let's take a look at the asymptote at minus pi over 2, or in this case, the suspected one. Now, we're only going to have to consider the limit as we approach minus pi over 2 from the right. And the reason is the function's domain does not contain any points to the left of minus pi over 2 and to the right of pi over 2. So we only have to worry about what happens as we approach minus pi over 2 from within the domain, and hence we're only going to consider the right-hand limit. So here we see it. Again, approaching minus pi over 2 from the right means we're looking at this limit. And so as we take this limit, we see that the 4/3 x gives no problem. This becomes actually minus 4/3 pi over 6. Put that minus sign in all the way through here. And the more challenging part is considering the limit as x approaches minus pi over 2 from the positive side of tangent x. We can write that tangent as sine over cosine if we like, or we can do this limit just from knowledge of the tangent that we're comfortable with. But we'll just take a look at this representation for just another option here. So one way to investigate this limit, let's take a look at the, and letting our x approach minus pi over 2 from the right means we're looking at angles that are coming down here, very close to right angles in the lower or fourth quadrant there. So we're looking at angles something like this. Okay. Now remember, the sine coordinate is the second coordinate of points like this. And if we're down here near this lower point of the unit circle, the sine coordinate is getting close to -1. And the cosine is the first coordinate for an angle down here in this area. The first coordinate is going to be, well, we're going to be very close to the vertical axis. So that first coordinate is going to be a small and positive number, positive because we're actually in the fourth quadrant, where that first coordinate is positive. So this particular limit looks like -1 over a small positive number, which suggests a large negative for minus infinity. And when we do the minus infinity, the net result is plus infinity. And so that verifies the behavior we suspected over here, that in fact this graph really is heading off to infinity as we approach that left side of the domain. You can do similar analysis, I'll leave it to you, to show that as you approach pi over 2 from the negative side. So in other words, we're now looking at coming in from this direction, that limit turns out to be minus infinity, and again goes along with what we see, that the graph seems to be diving towards large negative numbers in that area. So we'll update the graph, put in those asymptotes, now that we verified them. Next, we'll look at where the function is increasing or decreasing. Now we can see from the graph that the function appears to decrease as we start from the left of the domain. It then starts to increase a little bit and then decreases again as we approach the right end of the domain. Where does the function change from decreasing to increasing? Well, that's not clear from the graph. We can see about where it happens, but to really pinpoint those changes of direction, we're going to need to use the derivative. So increase and decrease is related to whether the derivative is positive or negative. So let's take a look at dy dx. Differentiate 4/3 x minus tangent x, and we get 4/3 minus secant squared x. If we want to find out where the derivative or any function is positive and negative, the first step is to find out where that function is 0. So where does dy dx equal 0? Well, setting the derivative equals 0 gives us secant squared equals 4/3 x. So secant will be plus or minus 2 over root 3. Or if you're more comfortable with cosine, we can write cosine is minus root 3 over 2. Now here's where the domain becomes important. Let's again take a look at the unit circle. And again, our knowledge that the cosine is the first coordinate of a point on the unit circle. So the first coordinate will be minus root 3 over 2 over here. Here's the minus root 3 over 2 line. Or if the cosine could be root 3 over 2, that'll correspond to a first coordinate value over here, root 3 over 2. Now remember, we're only concerned with angles between minus pi over 2 and pi over 2. So there's no way such an angle is going to reach over here into the second and fourth quadrants. So for values in our domain from minus pi over 2 to pi over 2, this cannot happen. There won't be any points where the cosine is minus root 3 over 2, and so we're only going to consider the plus root 3 over 2 possibility. That's the only one, again, that holds up in our domain. For those, it turns out root 3 over 2 was one of the nice values of the cosine that I hope you recognize. The cosine of root 3 over of an angle is root 3 over 2 if that angle is pi over 6 or minus pi over 6. Again, just taking the values that are in that range from minus pi over 2 to pi over 2. So this gives us two possible critical points. Well, they are critical points because they're derivative of 0. They're not possible critical points. This gives us two critical points, and we're going to graph those on the number line within the domain, and now determine on each of the three intervals formed whether the derivative is positive or negative, and hence whether f is increasing or decreasing. So, as usual, we're going to check one value of the derivative at each of these intervals. So in the first interval here, a nice value corresponds to minus pi over 4. And if we put minus pi over 4 into f prime, we see we get down here 4/3 minus sine squared at pi over 4, or secant squared of pi over 4. The secant of pi over 4 is root 2, so this becomes 4/3 minus 2, and hence that turns out to be less than 0 by this calculation. Between minus pi over 6 and pi over 6, the easy value is 0. If we plug 0 into the derivative, and remember that the secant of 0 is 1, we get 4/3 minus 1 for this calculation, and that turns out to be positive. And then likewise, we get a negative value when we plug 4/3 in to account for the last interval. So this shows us the function is decreasing on the two intervals from minus pi over 2 to minus pi over 6 and pi over 6 to pi over 2. It increases on the third interval, the one between that goes from minus pi over 6 to pi over 6. And so that really nails down these turning points here where the function changes from decrease to increasing and increasing to decreasing. And of course, knowing where the function's increasing, decreasing tells us about the critical points. It means the critical point at minus pi over 6, the one over here to the left, has to be a relative minimum because the function falls as we approach it from the left and then rises as we leave it from the right. Okay. It's often important to plot these critical points, so we now know the x-coordinate. To get the y-coordinate, we plug the critical point, the critical number, minus pi over 6, into the function, the original 4/3 minus tangent x. We've done that down here. Use the fact that tangent of minus pi over 6 is minus root 3 over 3, and that gives us a final calculation value of about minus 0.12. So this is a small negative number, and of course that confirms what we see here about the low point being a little bit below the x-axis. Likewise, we can fill in the other critical point. At pi over 6, we get a y value of about 0.012, a positive value a little bit above the x-axis, and of course that's a relative maximum. Move on to concavity. We want to take a look at the second derivative. So for the second derivative, we have to differentiate the first derivative, and to differentiate secant squared, that's a chain rule problem. We have minus, and then differentiating the secant squared, we have twice secant, that differentiates the square, and then times secant times tangent, which differentiates the secant function. And this simplifies into minus 2 secant squared tangent x. Where is this equal to 0? Well, it's a product of two functions, so it's going to be 0 only when one of those functions is 0, and the secant of x is never 0. Secant of x is 1 over cosine, and if you have a 1 in the numerator, or anything non-zero in the numerator, the function is not 0. So the second derivative is 0 only if the tangent of x equals 0, and again, we're on this interval, the domain minus pi over 2 to pi over 2, and the only place tangent of x is equal to 0 on that interval is at x equals 0. So as before, we now use the second derivative of 0 to cut the domain up into now two intervals, minus pi over 2 to 0 and 0 to pi over 2. We want to check the sign of the second derivative in this case. So again, we can do that now by plugging in just one point in each interval. So if we plug in minus pi over 4 for the interval on the left into the second derivative, this calculation gives us minus 2, And again, the secant of pi over 4 is root 2, so square it gives 2. And the tangent at minus pi over 4 turns out to be minus 1. So this gives us an answer of 2, and, or excuse me, 4, and that turns out to be positive. And then likewise over here we can plug in the value, that should have been plus pi over 4 over here. And we finally get a value of minus 4 in that case, which is negative. So this tells us now that the function is going to be concave up on the interval from minus pi over 2 to 0. And of course we see that over here, and then concave down over here. So there's just that one inflection point. The concavity changes from up to down at the point 0, 0. So 0, 0 is also playing the role of an inflection point. Now, a few other features of the graph. You've probably noted this pleasing symmetry. This graph is symmetric about the origin. And that means that if a point AB is on the graph, then the point minus A minus B is on the graph. So a point up here, maybe here's the coordinate AB. If we then negated the two coordinates, it would just flip us around the x and the y-axis to this point here. Now you can actually anticipate things like that by studying the function. Graphical symmetry about the origin occurs when you have an odd function. You may remember from algebra that a function is an odd function if when you plug minus x in for f and do some algebra, you simplify to minus the original f of x. And this has to be true for all x in the domain. This is the case for this function, so let's go ahead and put minus x in for x. And so we have 4/3 times minus x minus tangent of minus x. This gives us minus 4/3 x. The tangent also, in fact, is an odd function, so tangent of minus x is minus tangent of x. And we can then factor a minus sign out and see we do come back with minus f of x. So we could have predicted this symmetry from the graph by checking earlier to see that this function is an odd function. And there are also even functions. A function's even if g of x, a function g is even if g of x is equal to g of minus x for all x in the domain. And for graphs of functions like this, those graphs are symmetric about the y-axis. So it might be a good idea to keep these symmetry ideas in mind too, because again, if you know symmetry, they can really add to the ease with which you might have to produce a graph. Now, we've seen that we have these graphing calculators, so this example that we just finished showed you can use the calculator to fill in specifics about the graph. Why else might you need to know all this stuff about the derivatives and calculus? Well, graphing calculators they're wonderful tools, but they can't answer all our questions, and you really have to be careful with what you see, how you interpret it. So here's one example. Back in chapter 2, we considered limits, such as the limit as x goes to 0, 1 minus cosine 25x over 0.3x squared. What we see over here is a picture of what came out when I used Mathematica to graph 1 minus cosine 25x over 0.3x squared on a very small interval containing 0. Now, if you saw that, you might think, boy, this function jumps all over the place. So because of that, it doesn't look like it's settling down to one number, and so we might be suspected, or we might suspect the limit doesn't exist. However, you can use chapter 2 methods. Might go back to be a nice review for the final, to calculate this limit, and you get 3125 over 3. Of course, you can also experiment with other graphs. There are other graphs that will show you the correct limit, although it'll be in decimal form, so it might be a little hard to predict this particular value. Okay. So to answer the question, what's going on here? Why does the graph look like this? Well, you need the tools of calculus to answer questions like this. This gets into an area called numerical analysis, among other things. But anyway, keep in mind that you gotta, really be thinking constantly when you're working with your graphic calculator and trying to draw conclusions from graphs. We had another nice example of this in class. We worked on the project on Richard Feynman's mental calculation of the cube root of 1729 over 3. And after doing that project in class, we looked at the graph of y equals cube root of x and the linearization of the cube root at the point a equals 1728, which was the nice value because the cube root of 1728 is 12. So the graph up here shows the graphs of both functions on one graph. And again, if you're not aware of what you're doing in terms of calculus, it's hard to know how to interpret this picture. First of all, the line looks like it has a slope of about minus 2/3, not 1 over 432. And so there is a reason you always want to be aware of the scale on your y and x axes. There's quite a big spread of change of 4 on the y-axis, on the x-axis down here, but only a very small change on the y-axis. So again, the calculator distorted this graph and might fool you if you're not really careful about what you're looking at. And of course, this looks straight, but if one of these graphs is the graph of the cube root, that is really not a line. It actually is concave down, so it bends, and it would take calculus to discover this if you're trying to look at the graph. Okay. Finally, solving the case in problems involving the physical world, you can say things about the derivative or second derivative of a function you're curious about, and it may be very, very difficult to find information about the function itself. So as engineers and scientists, you'll deal a lot with what are called differential equations. So these are equations that give information about a derivative or second derivative for a function, things like this or like this. And one of the things you'll be doing in those courses is if you can't solve these equations to figure out what the function r is or what the function s is that you will use these expressions for derivatives to find out some things about the function and its behavior. In this first case, you can see that if absolute r is greater than absolute t, then r squared is greater than t squared. So r squared minus t squared will be positive, and so this function will be increasing when absolute r is bigger than absolute value of t. It'll be decreasing in the other case where absolute value of r is less than absolute value of t. In the second case, we have information on the second derivative. Minus 4 theta squared can never be positive, so it's going to be negative. And so in this case, we'll know that whatever this function looks like, it's going to be concave down. So keep these applications of the derivative in mind, not only for analyzing graphs, but also thinking about functions. And again, when you use your calculators, keep these things in mind so you don't get fooled by a deceptive picture in your calculator. Thanks. See you in the next video.